my name is Joe Winston. I'm the nTopology Account Manager at Measurement Solutions Limited. Today, I'm going to give you a quick introduction to nTopology platform. I'm going to show you a few slides to give you a brief overview of the company and some background of how the software actually works. Then we'll jump into the software itself, and I'll show you some live examples of not only what the software can do, but just how quickly and robustly it can perform some really complex operations. So first, a quick background on MSL. We were founded in 1998, predominantly focused on metrology solutions. In the early years, we built a large customer base with not only CMM equipment, but also support and calibration services. The development of more complex geometries created a demand for 3D scanning, not just for inspection, but also for reverse engineering. And this is where MSL's relationship with Careerform began. We're the UK reseller for Careerform, and it's enabled us to expand our customer base to over 1,000 UK customers. nTopology was a natural fit with our existing customer base, and it's enabled us to offer an end-to-end solution from scanning a 3D part to optimizing in nTopology through to inspection of the final part. So who are nTopology? The company was founded in 2015 and quickly released their first software package called Element. Element was focused on lattice generation and manipulation, and it was aimed to fill a void where traditional CAD systems fell short in working with these quite complex structures. nTopology could really excel here because the software was based on a new and very unique mathematical architecture. And nTopology soon realized that Element's maths-based approach had advantages far beyond working with lattices. It had the potential to provide a whole new way of designing parts based on maths and data. In 2018, nTopology took all of its learning from Element and launched its beta version of Platform. Lockheed Martin were one of the first to see the potential of Platform, and they got on board with a $3 million investment. As further investments were secured in 19 and 20, even more features were added to Platform, giving engineers faster and more efficient tools to work with. nTopology currently employs around 120 people, mostly in the States, but they plan to expand quite rapidly in 2022. So although most of the guys are based in the States, they have some staff over here in Europe, and MSL are the UK reseller of nTopology. So what is nTopology? It's not an easy question to answer because it can't really be compared to the CAD packages that we know of today. To sum it up in one line, we would say that nTopology is a software company building the next generation of engineering design tools for advanced manufacturing. But what does that really mean? As a starting point, I actually find it an easier concept to grasp by explaining what it isn't rather than what it is. The name nTopology conjures up the idea that it's purely a topology optimization tool, but it's not. Neither is it here to replace existing CAD packages like SolidWorks and CATIA or simulation software like ANSYS. It sits alongside all of these existing CAD packages, allowing you to share data between all of them. And the idea of sharing data is a very important part of nTopology. By playing nice with existing software packages, nTopology is here to enable better workflows and help to create complex parts more efficiently and more robustly. So rather than a CAD package, we can think of Platform as an engineering environment where you can combine design, simulation, and manufacturing inputs, allowing a user to consider function, geometry, FEA results, and DFAM all simultaneously. So unlike traditional CAD packages, where we simply create a 3D model, in nTopology, we create a process built on the foundations of maths and data. This means that if we create a process to build a heat exchanger or a rocket nozzle, we never have to design another one. We only have to adjust our parameters to account for maybe a revised space envelope, and the workflow will automatically generate our new design. So why should we choose nTopology? With the advances of AM machines, materials, and expertise, we now have the ability to manufacture parts that are far more complex than we can effectively design using traditional CAD packages. It's really a stark contrast to where we were 10 years ago, where we could design parts that we couldn't really manufacture. So what we're saying is that nTopology is bridging the gap that we currently have between design and manufacture. And it's doing it with a smarter and a more efficient use of data. So let's break down what I mean by a smart use of data. When we think of early manufacturing, we think of someone in a factory manually making each individual part. But now we have machines that can create hundreds of parts in just seconds. Similarly, computing power continues to evolve and increase year on year. my watch has more tech in it than my phone did 10 years ago. And we wouldn't even consider a 10-year-old computer as good enough to design the complex components that today's engineering environments demand. Essentially, we've seen exponential improvements in manufacturing and computing, but design software is somewhat lagging behind, and it shifted the bottleneck from manufacturing to design. Traditional CAD packages are based on the same architecture as when they came into existence 40 years ago. And you could really go even further than that and say it's essentially a descendant of pen and paper. Okay, we've moved to a 3D world, but essentially CAD is a 3D version of historical processes, where a designer uses their best guess at how a system should work and creates a drawing for someone else to manufacture. But nTopology does things slightly differently, and this is why we think it's the next generation design tool. So we live in a world where data really is everywhere and it's everything. So why not apply it to designing parts? When we analyze and work with any other data sets, we have automated ways to process it. So I can create a spreadsheet in Excel or write a program that someone else can use to solve a complex problem. And this is the backbone of nTopology's design philosophy. With nTopology, rather than using computer-aided design, we're using the technology at our disposal, along with real data, and asking the computer to generate our design. Using computer algorithms, we can automate the creation of optimized shapes that a human wouldn't even dream of. And if they did, it would take them days, if not weeks, to create them. So nTopology has many unique features that differentiate it from traditional CAD packages, but there are three key elements that really set it apart. I'm going to give you a quick intro onto what they all mean before we break them down into a bit more detail. So implicit modeling is based on mathematical functions. Models are very lightweight, making them easy to store and work with, and the geometries are unbreakable. We can see this is a kind of real-time example of just how quickly we can manipulate and change a gyroid structure within a part. Field-driven design creates the ability to quickly process complex features and operations, and simulation data can be converted into fields, which can drive generative design. Reusable workflows, we touched on earlier, when we said that a workflow creates a process rather than a description of a 3D model, and it leads to repeatable and reusable customization. So in the example here, we've created a stochastic lattice, and within this workflow, we can apply it to each face that we want to apply it to. Because the implicit modeling and field-driven design create such robust models, we can regenerate these workflows and the model never breaks. So to go into a bit more detail on implicit modeling, it's a lightweight way of representing a 3D object using a mathematical function. So traditional CAD systems use BREP or body representation to define or describe a 3D model. It plots edges, faces, and points in space, which is fine for simple geometries, but it gets very complex very quickly with lattices, freeform shapes, and intricate support structures for AM builds. With nTopology's mathematical architecture, what you see isn't really a 3D model, but a graphical representation of a mathematical formula. And because we're just looking at mathematical formula, the geometries are unbreakable. So intersecting bodies, overlapping faces, and inverted surfaces are really just a thing of the past in implicit modeling. These are issues that you see quite a lot in traditional CAD packages. So think of it as a volumetric way of describing a shape. In the example on the right here, we have a mesh, a model which is represented as BREP, and an implicit model in nTopology. The mesh with a reasonable resolution is 100 megabytes, the BREP is 30 megabytes, and the implicit model is just 70 kilobytes. And this is very scalable. If we were to double the size of the part and keep the same resolution, the size of the mesh would increase quite dramatically. The BREP would also increase, but the implicit model, because we're just storing a mathematical equation, would stay at pretty much 70 kilobytes. So let's jump into the software now really quick. Give you more of a kind of graphical representation of what I mean by that. So here we have a few different models in front of us, and for some this is probably the first time you've seen nTopology's user interface. So as we'd see in normal CAD package, we have a ribbon across the top here, showing some of the functions and features. In the left here, where we'd normally see a design tree, we see a notebook. This notebook is made up of a series of blocks, each individual block here, and a series of blocks creates a workflow. So rather than building a part here, we're building a workflow or a process. So this is these are all the same bracket. So this bracket is imported as a step file. It's a brep, so we can see we have faces, we have edges, and we have points. This has been converted into an implicit model, this model here. So we can't select edges, we can't select points, but because it's a graphical representation of a mathematical formula, we can perform some really, really complex operations that happen very, very quickly. We can also convert into a mesh or an STL file. So this isn't a particularly high resolution STL file, but within nTopology, we can import and export STL files, import and export step files, and we work with implicit models. So just to give you an idea of how quickly we can perform operations with implicit models, I'm going to turn this bracket into a gyroid structure. So really, really quickly, we've turned that into a complete gyroid structure. And because we've built a workflow rather than a part, I can change it to my sphere. So I've changed my sphere into a gyroid. So that's a very quick intro into implicits. We jump back to the presentation and skip on to our next, field and data-driven design. So field is the idea that every point in space is represented as a distance. And by using maths, we can assign a positive or negative number to that point. So I heard this described really nicely the other day in the context of a balloon, so a balloon analogy. So if we take a look here, this is a section through a cube. Anything in this dark area is a negative value, anything outside is a positive value. So imagine blowing up a helium balloon in a room. So if we imagine the helium is a negative value, the skin of the balloon is our boundary, and any of the free air in the room is a positive number. So a field is a rule that associates a value to each point in 3D space. And because a field assigns a value to each point in space, we can easily switch a field for some real world data, like displacement values from static analysis, for example. We can also use data from heat maps, pressure maps, fluid flow, buckling analysis, really anything that you can extract data from can be plugged back into nTopology and used to create or modify designs. So let's have a quick look at that in the context of the software itself. So we're going to go back here and pick up where we left off with this sphere. So if I were to run a section through a sphere, we can see that it's a completely solid model. And if I show you the field, we can see that the boundary of the sphere, we have 0 value. Anything inside the sphere is a negative value. Anything outside is a positive value. Likewise, if I switch over to this cube and run a section through it, we can see that again, anything inside the cube is a negative value. At the boundary, we have 0 value. Anything outside is a positive value. And these contour lines go up in whatever interval I want them to. So I've set them to 1 millimeter. This is +1, +2, and inside -1, -2, etc. I can also shell this part. So now if we run a field, the shelled part, you can see again, anything inside, anything solid is a negative. At the boundary, we have 0 value. Anything in free space is a positive value. So we will flip back to the presentation once more. And look at our reusable workflows. So the concept of a workflow is very different to traditional CAD process. The idea that the implicit modeling and field-driven design create such robust models that it means we can very quickly reprocess parts. They're not going to crash, the models aren't going to break, so we can create workflows. So workflow applies a specific instruction or command to a geometry, and the author builds a process rather than building a part. Use cases, as you saw in the example just a minute ago, medical, so this stochastic lattice on this hip cup, for example. This can be really, a stochastic lattice can be really easily applied to a specific patient's data. Likewise, orthotics, we can create a workflow to build a cast or a custom orthotic. Then we just have to replace the scan data at the start of the process and we'll rebuild a cast or an orthotic for that specific patient data. Likewise, mass customization for protective products, helmets, and consumer products like trainers. So let's flip back to the software again, and I'll show you an example of what I mean by a repeatable workflow. So we started with this cube here, which we've already seen. And with this cube, I've created a shell. So I can quickly isolate the inside of the shell with a Boolean subtract. And I'm going to turn the inside of the shell into a lattice. So I just drag the inside, drop it into this lattice creation block here. And I've created a lattice in that void. Small Boolean operations, I can turn this lattice in this shell into one complete part. As we can see, at the intersection between the lattice and the shell, we have a sharp corner. So in a traditional CAD package, it would be quite a difficult and time-consuming operation to select all of these edges to put radiuses in all of these areas. But in nTopology, all I have to do is assign the blend radius that I want. Let's go for 0.5. And in less than a second, it's created a blend radius in all of those areas. In these corners here, the radiuses are really, really close to intersecting. This would cause an issue in BREP, or boundary represented models. But in nTopology, it's no issue at all. We can even make these silly, silly numbers. It's not going to break the model. It's just going to keep creating and keep creating. Now, if I were to change the size of the cube, so at the moment it's 10 millimeters, but I'm going to go up to 50 millimeters. So the original lattice that we had inside was, the cell size was 2 by 2 by 2, so it made 27 lattices. And here it's created 12,000 in just a few seconds. And again, all of these intersections between the shell and the lattice, we can really quickly change any number we want. We can modify the cell size. And we can change the lattice type itself. But what we've created here isn't just a cube with a lattice inside. We've created a workflow. So whatever I want to apply this shell and infill to, I can. So let's take our sphere, for example. I'm going to drop the sphere in at the start of the process. And in less than a second, it's run through exactly the same process with the sphere. So the sphere and the box are quite simple shapes, but let's try doing the same thing with the bracket. So something completely different geometry-wise, but I'm going to drag and drop it into the start of the process. And in just a couple of seconds, it has created that infilled, shelled and infilled model. So at this point, we have the model infilled with a lattice. We can change our beam thickness as well. Let's go to something that we can see that a bit clearer on. So the beam thickness now is 0.5 millimeter. I can really quickly change that to 2 millimeters, whatever size I want. The symbol here looks like a Wi-Fi symbol, means that we can drive this value based on some other data, and it kind of gives us a bit of an all-access pass to design. So what I might want to do here is create a ramp block, which is going to vary the thickness of these beams throughout the part. So at the start of the process, I want to add a plane that's going to be at the bottom of my part here. And with my beam thickness at 0 millimeters from the plane, I want my beam thickness to be 1 millimeter. And at 50 millimeters away from my plane, I want my beam thickness to be 3 millimeters. I'm going to change this with geometric continuity. All I need to do is drag and drop my ramp block into my beam thickness. And really, really quickly, we have, just going to change the lattice type to show it a bit more clearly. So we have a model where our beam thickness close to the plane is smaller and our beam thickness further away is bigger. So this is this may be useful if we want to have more strength in this area of the part. Maybe we want to evenly distribute the weight across the z-axis, so have more weight up here and less down here inside the part. But where this gets really interesting is when we can use it with real world data. So let's switch to our next instance of nTopology. No, let's not. Let's firstly switch back to our presentation. I'm getting all ahead of myself. So yeah, reusable workflows. So hopefully that gave you a good example of how nTopology can build a reusable workflow. So a few case studies of where nTopology is particularly good. Heat exchangers up here. There are huge potential in heat exchangers because we can import data from external programs. We can import fluid flow data and heat maps. We could then just assign a space envelope in nTopology, and we can let the software build the most optimized heat exchanger that it possibly can. Satellite bracket, aerospace and flying parts. We can use nTopology to reduce any material that we don't need, making the parts as light as they possibly can with as least material as possible. And mass customization or patient-specific devices. This is a medical product line where we print the implants for a specific patient and the surgical guides. So I'm going to get back into the software itself to go through a few more demonstrations. If you have any questions, feel free to drop them in the chat box. We'll try and get to them at the end. So, okay, let's flip back to the software. So we left off looking at how we can drive different properties of a part using real world data. So here we have a bike saddle. We've run a static analysis in nTopology, and we've seen that the areas of high displacements here and here are where the seat bones contact the saddle. Using this data, we can create a stochastic lattice, and we can tell the software to create a higher density lattice in the areas of high displacement and a lower density lattice in areas of low displacement. We can also use the data to drive the sizes of the beams. So in areas of high density, we can have much lower beam thickness to create a bit more cushioning. And in areas of low displacement, we can have a much thicker beam thickness. We can merge this together with the areas of the saddle that we want to keep, using some Boolean operations to create a perfectly optimized saddle. we can also do this with this example here of a brake pedal. So this is a completely solid brake pedal. This is just imported as a step file. So we can separate out the inside and the outside of the pedal. All I want to do is take all of this middle section out and replace it with a lattice between these two CAD faces. Where we're going to create a conformal lattice between the two faces. So we will first split the two faces out here and here, and we're going to create a cell map between the two. So here we can apply the counts that we want in the U, V, and W axis. We can really quickly change these if we want to, and we can apply the unit cell that we're going to use. In this case, a body-centered cubic. And when we combine these two together, we get this lattice structure here. We can change the beam thickness if we want to, very, very quickly. And with some Boolean operations, we can merge the lattice back to the pedal to create the part. Again, as we saw in the previous demonstration, we have sharp corners here where the lattice meets the outside faces of the brake pedal. But we can really quickly change the blend radius. In traditional CAD, it would take us a long time to select all of these faces. In nTopology, we click a button and it's done. All of the radiuses are in place. So we could either stop here if we wanted to. Maybe in a traditional CAD system, it would have already taken us long enough to create all these radiuses. But in nTopology, we're kind of only just getting started. So from here, we have taken all of the material, or taken a load of material out of here, but have we taken it away in the most effective way we possibly can? At the moment, we haven't. So what we're going to do is run a static analysis on the brake pedal. So we have meshed it, we applied a material, we're going to apply a displacement restraint in this area here, and we're going to apply a force on the pedal here. So the results of our static analysis show that we have areas of high stress here and areas of low stress here. We can use this to create an optimized lattice in the center of the part. So again, I'm going to take a ramp block, and for my scalar field, I'm going to use my stress results. I'm going to take the minimum value and the maximum values. And in the areas of low stress at the min here, I want to make my beam thickness 1 millimeter. And at the areas of high stress, I want to make my beam thickness 3 millimeters. And again, I'm going to change this with a geometric continuity. So now all I have to do is drag and drop my ramp block into my beam thickness block here. And we have created a model where the beam thicknesses in the low stress areas are much thinner. Beam thicknesses in the areas of high stress are much thicker. And I still have the ability to change my UVW count if I want. For example, maybe I want an extra row in this axis. Maybe I even want to change my lattice type. These are all operations that can happen really, really quickly. So now we talked about how we have created a reusable workflow here. And as it's a kind of that time of season, I'm going to import a completely different file into here. So I'm going to import a CAD model of an Easter egg. So now we have an Easter egg and a brake pedal, which are two completely different geometries. They couldn't be more similar. But with nTopology, I can take my CAD faces from my Easter egg. I can use my external face That's the top face. Use my internal face. That's the bottom face. I can change my UVW count, and using the same process, I can turn my Easter egg into a conformal lattice. Change my beam thickness. I can change my lattice type. I can change my UVW count to whatever I want it to be. And we've created an Easter egg instead of a brake pedal. So just an example of how robustly the workflows can change. It doesn't matter what the geometry is. They don't have to be at all similar, but we can run very different parts through the same workflow. Okay, so let me switch my screen to the next example, which is going to be this automotive bracket. So this is a part that we've imported as a step file, imported from our CAD system, and we've converted the body into an implicit model. We're going to take all of the interface regions, so we're going to use these for our static analysis a little bit later on. So we have meshed the part, we've turned it into a volume mesh ready for FEA and topology optimization. The first thing we're going to do is run a static analysis to see where all the areas of stress are. And then we're going to run a topology optimization. So it's kept all the material in the stress paths. In traditional CAD systems, this is where it can get quite complex to remove all of these sharp edges. But in nTopology, we have a smoothen body block, and we can really quickly smoothen out the result to make a nice looking shape, nice faces. We can see that we've lost some of the interface sections here, but with the Boolean that we took earlier of all of these interface sections, we can merge everything back together. So we have some nice edges, nice intersections and interfaces where we want them. From here, we can mesh the model. We can quadrangulate it to create a model that's CAD faces. And this model can be exported out as a step file to go back into whichever CAD software you want to put it into. Or we can use the mesh to run a static analysis of the new topology optimized shape. We can see here the areas of high stress and the areas of low stress in the topology optimized shape. And as long as the stress values are within the limits that we've set, we can do a bit further modification of this design. So again, we've got some ramp blocks going on here, and we have variably shelled this part. So in areas of high stress, we have much thicker wall thickness. In areas of low stress over here, we have a much thinner wall thickness. So we've set our ramp block to do that for us. Now we can go a step further than this and infill all of the hollow with a lattice. Again, with a ramp block, we can use the stress analysis that we've just run to assign beam thicknesses to the lattice. So again, in areas of high stress over here and at the edges here, we have a much thicker beam thickness. And in low stress areas in the middle, the beam thickness is much thinner. We can see that here. So we have a much thinner lattice in the middle and a much thicker lattice at the edge here. And then again, once we've completed this with the lattice infill, we can run another static analysis to verify these results, or we can export it out as a step file to go back into our native CAD software. So with topology optimizations, we have, I'm just going to switch to another nTopology. So this is a topology optimization that we've run in nTopology. And these are all the blocks that go into setting up the optimization. In the end, we get our final part here. What we can do in nTopology is very quickly package all of this workflow up into one simple block. So everything here, I have packaged up into a very easily digestible custom block here. So I'm going to import my step file. And I'm going to use this block here to do a very quick topology optimization. So it's asking me to select a CAD body, which I've just done. I'm going to select a load face, and I'm going to select a couple of restraint faces, one here and one here. We have a pre-populated force, which we can change if we want to, but this is right for this particular model. And we have some parameters here to do with the topology optimization, which we can change if we want to, but in this case, I'm going to just leave them as they are. And in just a few seconds, this is going to come back with a topology optimized result of this particular part. So if you have someone within the company who can create workflows for you in topology, we can package them up into a very simple block and share these between other areas of the business so that everyone has access to topology optimization. And there you go. In just those few seconds that we've been talking, we've created a topology optimized bracket. And we can keep doing this. We can drag in some more parts and create a duplicate of this block to create more and more topology optimizations. So the last example that I'm going to share with you, so I want to leave some time in case there's any questions at the end, is we talked about in the presentation potential medical applications. So this is just kind of a very rough sketch of what a cast could look like, but with nTopology, we can really quickly change the lattice type of this particular cast. We can change a lot of different features in it, but we can also take a patient's scan data. So this is an STL file of a patient's arm. From here, we can convert it into an implicit model, and we can create an area around the scan that we want to create a cast. And we can create a Voronoi lattice and create the area of a cast that fits perfectly over another patient's scan data. Now, if we want to make the exact same cast, but for a different patient, all we'd have to do is import the scan data of the next patient, drop it into the start of the workflow, and we're going to create a bespoke cast for the next patient. Something else we can do in nTopology is say, for example, the site of the injury is over the scaffold area here, an injury that I know about very well. We can assign this sphere to that site of the injury, and we can create another ramp block. So we can drive the spacing of this lattice to be much more dense around the site of the injury and much less dense areas further away to create a bit more support in this area. And if we were to do that, we would create something that looks a bit like this. So in areas of, I'm going to open up the ramp block to show exactly what I did at the injury site at 10 millimeters or anything up to 10 millimeters. We want the spacing in our lattice to be 8 millimeters, and at 100 millimeters away, we want our spacing to be 15 millimeters. And that's how we've created this cast with varying spacing. So I think that is about it for demo, and I'm kind of acutely aware that we only have around 10 minutes left. So switch back to our presentation. And I will let me have a quick look and see if we have any questions come in. Okay, so if anyone does have any questions, then please drop them in the comments box or in the chat box, and we will get to them. I have one here. In building a workflow, is it best to use a simple geometry part to develop the elements in an easy way to understand, where you can see the effect before introducing that workflow to a more complex geometry? Yes, in a word, that's how I would, or that's how I've come up with the workflows that I've done already. With simple geometries, it's almost instant to do quite complex operations in nTopology. The more complex the geometry becomes, the workflow becomes slightly more complex. But yeah, it's definitely easier to start with something simple and create the workflow with a simple part, and then introduce more complex geometry once you're kind of completely happy that the workflow is doing exactly what you want it to do. Hopefully that answers that question. Okay, so I don't think we have any more questions. I am, in that case, I'm going to go into one more instance of nTopology and just show you one more example of the GPU acceleration, how quickly we can change parts kind of on the fly and live, if you like. So here, these are just a series of cubes that we've created in nTopology using the Create tab at the top here. We have a sphere and we have a series of cubes. So these are created as a Boolean union with a blend radius between all of them. Now, if I drag my sphere, which is currently set to the same center point as this first cube, if I drag my sphere, we can see how quickly the kind of the visualization works within nTopology and how quickly we can change designs. This is not a particular design that I think anyone particularly come up with, but this is just to show the example of how quickly the software can work, how quickly it can update. I can change the blend radius in here to something a bit larger. And again, I can drag my sphere around and it's going to create some really weird shapes, but it will show you how quickly it can update. Where this gets a bit more complicated is when I change my cubes into various different lattice structures. And again, I can drag and drop my sphere and it's going to really, really quickly update in kind of real time and show you sort of how the geometry modifies as we move everything around. So yeah, just a kind of very quick visualization of how quick the software can update and how quick it works. So I'm going to jump back in and see if we've got any more questions. And if not, which it doesn't look like we have, I think that pretty much concludes what we wanted to talk about today, really. Hopefully everyone's learned something and found it useful. It's kind of our first venture, or my first venture into an nTopology webinar. So I would welcome any feedback or any other questions that you might have. Feel free to drop me a message. My email is at the start of the presentation rather than at the end of the presentation. Let me just whiz back to my email here. Feel free to reach out. Like I said, any questions, any comments, I'm more than happy to hear them. If there's anything particular that people want to see during the next webinar, we've got plenty more planned for the future. So if there's anything particular you want to see, then please let us know. But until next time, thanks everyone, and we'll see you again.